Let's apply Hess's law to a problem. This particular problem comes from page 269 in your book. It's number 59. And in this we're given the change in enthalpy for two small reactions and asked to calculate the change in enthalpy for a larger reaction that has multiple steps in it. We're then asked to use this change in enthalpy we calculate to decide if this would be an effective way to make ammonia. The first thing is to figure out how these reactions happen together in order to make this reaction. The first thing we should see is the ammonia here is a reactant, but we need it to be a product, so we are actually talking about that reverse reaction. We're talking about nitrogen and hydrogen combining to make ammonia. You do not have to write out these steps, but I like to show the logic and the thought process, and it might help you later when you go back and are studying for tests and stuff to see what you did. Because we're reversing it, the delta H is reversed as well. It's negative 46. If we look at the second reaction, it's hydrogen and oxygen making water. But in this one, we have water as a reactant, so we need to switch this one as well. And because we've switched this one as well, it now becomes positive 484 kilojoules. So we have the steps in the right order right now, but we have to figure out the amounts. We need the coefficients to be the same. I like to start with the largest coefficient. We need 6 waters, so we need to multiply all of the coefficients in this by 3. We need this reaction to happen 3 times to give us 6 waters, 6 hydrogen atoms, and 3 oxygens. And if we multiply our change in enthalpy by 3 as well, we get 1452, and it's positive. For the reaction on top, in order to make 4 ammonia molecules, we're going to multiply them all by 4. So 4 times a half gives us 2. 4 times 3 halves. We do 4 times 3 gives us 12 over 2, which reduces to 6, and 4 ammonia. If we look at our reactions now, we have 6 hydrogen here and on this side, so we can consider those canceled out. Because if the same amount goes in to the reaction as comes out, then it might as well just not be reacting. We can ignore it. If we're finding our delta H, we have to add it up. I forgot to multiply this by 4. So that will give you 184, negative 184. The change in enthalpy for the entire reaction is 1452 kilojoules plus negative 184. This gives us 1,268 kilojoules. And you might think about significant figures here, but you are adding and subtracting, so it's about decimal places. We would not round this to 3 significant figures. We would round it to have no decimal places. The second part of the question says, given this delta H, is this a useful reaction to synthesize ammonia? And it is not. This is very endothermic. That's a lot of energy that has to go in to make this reaction happen. Let's look at a second example. This example is from the same page in your book, but instead of having 2 parts, we can see all 3 parts of this reaction. Let's start with the easiest one first. We know that this reaction is going to happen in that direction because we have nitrogen monoxide and nitrogen dioxide on the right sides. So let's go ahead and write that. We also know that we are not going to change these coefficients because 2 of them are already correct. We'll have to change them elsewhere to get rid of this O2 and this ozone. O3 is called ozone. In order to cancel out this ozone, we need something that makes ozone. In order to make ozone, we have to flip this one up on its head. So we get 3O2, making 2O3. And because we flipped it, the change in enthalpy becomes positive. And finally, we need to have O by itself as a reactant, not the diatomic form. So we are also flipping this one. And I wanted to point out this change in enthalpy makes a lot of sense because the definition of a diatomic molecule is that it would prefer to be with a second one as opposed to by itself. So it releases energy when you put them together because it is easier to be in that state. Let's cancel out our ozones first. We've talked already about how we're not going to change these coefficients. So instead, we have to figure out how to get this to be 1. We're going to multiply by a number, but it doesn't have to be a whole number. We're going to multiply all these coefficients by 1/2. So half of 3 gives you 1.5, and half of 1 gives you 1. If we multiply this by 1/2, we get 213.5, and still positive. And this, we need 1 oxygen all by itself. So we're going to multiply by 1/2 again to give us 1 and to give us 1/2. That makes this change in enthalpy 247.5. And if we look, we can see that our ozone, our O3 cancels out. We have 1 reactant and 1 product. Our diatomic oxygen, we have 1 here. But we also have a 1/2 here. So we have 1.5 on this side and 1.5 on the other side as well. This gives us nitrogen monoxide plus a single oxygen, making nitrogen dioxide, and that's it. To find our delta H, we just add up the individual ones. So we have -199 plus 213.5 plus -247.5. When you add these up, you get -233 kilojoules is the change in enthalpy for this reaction right here.